Okay, so I'm going to take some waveguide measurements for you today. The primary measurement I want to take is to confirm the phase velocity and the lambda of the guide calculation. So we're going to use the slotted line. It's a little different on a waveguide. Let me show you a little closer. So the slot in the waveguide is cut in the top. Remember, the E field is vertical, TE10 mode, and so this slot actually doesn't interfere much with the TE10 mode because the electric fields, which are vertical, can easily terminate on the sides of the slot. And so we just gradually open the slot. You can see it starts out very small, gets a little wider, and then gradually goes back to a solid guide at the end, or solid piece. So just like the horn and just like the load that we saw before, as long as we don't make the transition of the geometry too extreme, we're not going to cause a mismatch. Now what is going to cause a mismatch is I'm going to put a load or a short on the line. Now the short I'm going to use is a sliding short. So the moving short is just as you would expect it. It's a solid piece in the waveguide. Now you might say, well, why don't we just put a little cap there? Well, the nice thing we can do with the moving or sliding short is if I unconnect it and move it, I can actually put this short where I want. So I can essentially adjust the phase similar to what we did in stub tuners. So by positioning the short someplace in this line, I can adjust the phasing of the voltages at this point. Obviously, if I'm lambda for away, it'd act like an open, and vice versa. Lambda over 2, it would look like a short. But we're just going to treat it as a direct short, put it on the slotted line, and then measure the VSWR, the peaks and valleys on our VSWR meter. I'm not going to take full VSWR measurements for every frequency because that would take too long, but I'm going to go through the waveguide frequencies that are appropriate. Remember, this is WR90 waveguide, so WR means it's waveguide rectangular and 0.9 inch. The typical use frequencies are 8.2 to 12.4 gigahertz. Below that frequency you get into cutoff. Actually, cutoff is 6.5 gigahertz. So I might start down in the 7 gigahertz range just to give you more complete data. The upper frequency limit, there actually is none with waveguide because we can see through it. If we can see through something, obviously light can pass through it. So all those frequencies up to light frequency are possible. But we don't like to operate more than 2 times the cutoff frequency because then we can have multi-modes develop, like the TE20 mode in the horizontal or TE101 mode in the vertical. TE20 is the next mode that usually develops because the waveguide is usually less than half as high as it is wide. And that means the TE20 would develop before the TE01 mode. And again, the reason why we want to avoid those higher order modes is that this probe would not work for TE20 because the waveguide TE20 means we'd have positive, 0, negative, and then 0 at the waveguide walls. So in the middle would be 0, and we were measuring 0. Down the middle of the waveguide, sorry. Okay, well, I'll set it up and then we'll take some measurements. So I've mounted the sliding short and I've positioned it so that I have a null at this location on the slotted line. And as I move this, you'll see that the signal will rise, indicating we're going from a null to a peak. And so I'm going to record various nulls and peaks along this waveguide and mark their position. And then from those two positions we can determine the lambda along the guide, which is related to the phase velocity. I'm starting at 8.5 gigahertz, and I'll go every half gigahertz up to over 12. So here's the data collection from the waveguide. The top orange is the WR90. It calculates the width, convert to millimeters, and then to meters, and then calculate the cutoff frequency, which is 6.56 gigahertz. Then the data, I started down here at 8.5 in the yellow, 8.5 gigahertz, and then I measured null values at each position I could on the waveguide. Null values are easier to measure than peak values, and then between nulls, of course, is lambda over 2. For some frequencies, I was able to measure 4 nulls, even up to here. I hit 12 gigahertz. I got 1, 2, 3, 4, 5, 6, 7 nulls being able to be measured. As frequency goes up, then it's easier to get the null measurements. Frequency goes down, so I went back down after I got to 12.5. The sweeper can't go over 12.5 unless I change the unit. But if I come down here at 8, I could only get 4 nulls, and then 7.5, only 2 nulls, and at 7 and 6.9, I could only get 1 null measurement, or between 2 nulls, for lambda over 2. So I calculated the lambda over 2 values when I had more than 1 null, or more than 2 nulls. I could calculate an extra value and then average out a lambda over 2 value. That gave me a lambda value and a velocity of propagation, and then based upon the frequency I could calculate the phase velocity, which leads to this classic curve that shows as you get closer to cutoff, now the wave is traveling, the angle of incidence is more straight up and down, and so your the wavelength you measure corresponds to a much higher velocity of propagation, and actually greater than the speed of light, which is referenced here as 1. And of course that's not a true value, but you can get to the actual guide velocity by dividing this value from c squared. So c is in the middle there at 1. But that's a pretty classic looking velocity, phase velocity, and group velocity set of curves. So I'll give you this data, and then you're going to be able to plot with that data the velocities we need.